Hello APC Mechanics students in Unit 5 Rotation, Class 9, 5.3 Rotational Dynamics, Part 1. Section 1, Rotational Kinetic Energy. Kinetic energy is the energy due to motion. For translational motion, it's given by K is a half mv square, where V is the speed of the object. We're interested in introducing the kinetic energy for rotational motion. This can be done by analogy. So as we have mentioned previously, that analogy is a promising approach in different topics in physics. Referring to our previous table, then what is the analogy between translation and rotation? The force is promoted to torque, the mass is promoted to inertia, acceleration A is promoted to angular acceleration alpha, F net is ma would be given by tau net is I alpha, velocity V would be given by angular velocity omega. Based on that, so if the kinetic energy for translation is given by half mv square, then m will be replaced by I, v would be replaced by omega, and by that our kinetic energy would be set up as half I omega square. Hence the rotational kinetic energy can be built up by analogy as half I omega square, where half I omega square is the rotational kinetic energy and the SI unit would be joules. I is the moment of inertia, and at this point we know that it's given by kilogram meter square, and omega is the angular velocity. Now section 2, translation and rotation, combined motion known as rolling. Consider a wheel object that is rolling. So by rolling means that the disk performs two types of motion, translation and rotation. It rotates around its axis while it's being translated. Rolling is a combined motion of translation and rotation. In this particular case, the wheel, which is the object, possesses two types of kinetic energy given by half mv square, where v is the translational speed of the wheel, or we say that it's the speed of the center of mass of the disk or the wheel itself, and the rotational kinetic energy given by half I omega square, where omega is the angular speed of the wheel. Then in this case, the kinetic energy is the sum of both energies given by half I omega square plus half mv square. So here, because the wheel is performing two types of motion, then it admits two types of energies given by half mv square and half I omega square. Alright, so this is it for section 2. Now section 3, rolling without slipping. This is very important. The combination of linear and rotational motion is known as rolling. Consider a wheel or a disk of radius r rolling on a level surface. Such type of motion is characterized by two variables of motion given by the angular velocity omega and the translational velocity v, or v of the center of mass. Generally speaking, there is no mathematical relation between omega and v at this point, which makes the motion rolling. So what I'm trying to say here is that the wheel can rotate around its axis with an angular velocity omega, and it can translate with a translational velocity v, or the speed of the center of mass, such that omega and v are independent. So take for example, the wheel can rotate around its axis 100 radians per second and translate for 1 centimeter, which means that the proportionality between the angular velocity and the translational velocity is not correlated. Or in other words, the wheel can rotate and translate independently, in which omega is different than v. Now, one specific class of such type of motions is rolling without slipping. Rolling without slipping is when the wheel rotates about its axis without any sliding between the object and the surface it is in contact with. Any angular rotation would cause translational motion, as seen in this animation. So here, previously I was trying to explain that both types of motion, translation and rotational, generally speaking, they are independent. If we're talking about rolling without slipping, now you can notice that the wheel will rotate, but this rotation itself will cause translational motion, and this is known as rolling without slipping. So rolling without slipping is when the wheel rotates about its axis without any sliding between the object and the surface it is in contact with. Then therefore any angular rotation would cause translational motion. In this particular case, we have v is equal to omega r. So basically the omega that we have introduced previously and the v that we talked about, if we're rolling without slipping, then they are related by the radius r, as we always know, where v is the translational speed of the wheel or velocity of the center of mass. This is known as the condition for rolling without slipping, and omega in this case would be the angular velocity of the disk around its axis. Moreover, if we split the rolling motion into translation and rotation, we notice the following. So for translation, all points of the disk translate linearly with the speed of v center of mass. So in the case of a translation, all points of the disk, they are being translated to the right with v of the center of mass. For rotational motion, what do we notice? That the disk is being rotated around the axis of rotation, which is this point, by a velocity given by r omega. So this point is not moving. The upper point is moving with the velocity r omega to the right, and this point, which is the point B, will be moving to the left with a velocity given by r omega. So let me here do just a recap. For the translation, all points of the disk are being translated to the right with the velocity v center of mass, whereas for rotation, let me consider point A, point O, point C. O is the pivot, or the axis of rotation of the wheel. Now the point A is moving to the right with the velocity r omega. The point C is moving to the left with the velocity r omega. If we combine the motion as for the rolling motion without slipping, we notice that the rolling motion, so here we need to make use of the fact that v is related to omega by v is equal to r omega, because the type of motion is rolling without slipping. The upper point of the disk moves with the translational speed to velocity of the center of mass, because the velocity is an additive vector quantity. So if we add these two factors, this is equal to v. So the total velocity would be 2 multiplied by r omega. The axis of rotation would be moving with a velocity given by r omega, because this is v center of mass, which is r omega. And here the velocity is 0. Now, what about the point which we suppose that it will be in contact with the surface? The velocity would be 0, because we would have a cancellation effect between this one and this one. So the point of contact indeed between the disk and the surface is momentarily at rest. Now here there is a very important question that we should ask. What is the cause of rolling without slipping? In fact, the force responsible for this type of motion is static friction. Static friction from the surface grips the bottom of the wheel, and it holds that particle point momentarily at rest. So the direction of motion to the right, then at this particular point the direction of static friction would be to the left. Why it is static friction and not kinetic friction? Because momentarily this point will be at rest and the wheel will roll to the right in this case. The remaining particles of the disk rotate about that pivot point. So here we're considering rotation about this pivot point and not the axis of the wheel itself. So we're assuming that the wheel is rolling around this pivot point. And now for the rest of the video, we're gonna solve some exercises. Exercise 1, a hoop of mass m and radius r rolls. So rolls means we have two variables given by v due to the translational motion and omega due to the rotational motion with constant speed on a horizontal surface without slipping. The moment they mention without slipping, then v is equal to r multiplied by omega. R multiplied by omega, where r is the radius of the hoop. What is the hoop's translational kinetic energy divided by the rotational kinetic energy? So we need to calculate the ratio of the translational kinetic energy given by half mv square to the rotational kinetic energy given by half I omega square. Now let me express this in terms of the translational. So that would be half mv square. We know that the rotational inertia of a hoop is given by mr square. So remember that for a hoop, it would be given by mr square. And for a disk, that would be given by half mr square. And always remember that the hoop is more inertial than the disk, and this can be found on your information sheet. That would be v, that would be r, multiplied by omega. Omega is v over r, square. Now this cancels with that because we have to the power 2, then that would be half mv square divided by half mv square, and the ratio means that this is 1. And remember that all quantities in physics have unit. This happens to be unitless or dimensionless because it's a quantity or a ratio between two quantities that are of the same unit, and C would be the correct answer. Which means that whenever a hoop is rolling without slipping, the ratios of energy between the kinetic between the translational and the rotational is divided equally between both. A wheel of mass m, which has a rotational inertia I and radius r, rotates with angular speed omega about an axis through its center. A retarding force F is applied tangentially to the rim of the wheel. The retarding force F finally stops the rotation of the wheel. Now, because the wheel is just rotating, then the energy admitted by the wheel initially is given by half I omega square, and we don't have any other form of energy. If the retarding force F finally stops the rotation of the wheel, which of the following best represents the total reduction in the mechanical energy in the process of stopping of the wheel? Now, what is the mechanical energy? Mechanical energy is kinetic plus gravitational potential plus elastic potential. We don't have elastic because there is no kind of springs. Gravitational, because we assume that the motion is symmetrical, so that would be also, you can ignore it. So it's only kinetic. Kinetic might be rotational or translational. They didn't mention anything about the translational. So the total reduction in mechanical energy from half I omega square to 0 would be E. Now a motor drives a shaft of radius r over 8. So the motor is being applied at a radius r over 8 that is attached to the center of a wheel of radius r. The motor is turned off and the force that the motor exerts on the shaft F motor varies with time as shown. So here what's happening is that a motor is driving initially a shaft, but it's being applied for a radius r over 8. Why this is important? Because the torque produced by the motor would be the force of the motor multiplied by r over 8. Now here notice carefully the magnitude of the force of the motor decreases linearly. There is also a constant friction force of 0.4 newtons applied to the rim. So why this is important? Because we know that this is the wheel, the rim would be this point, so the force, so the friction would be producing a torque given by 0.4 multiplied by r in the opposite direction of motion. So here we're talking about two torques being applied in opposite directions. During which time interval does the rotational kinetic energy increases, then decreases, and this happens whenever the torques are balanced. We expect that previously the torque produced by the motor should be greater than that produced by friction. When they are balanced, after that the torque produced by the friction is greater than that of the motor. So for that, let's equate both torques. The torque, and here we're assuming, since they didn't mention anything about the angles, we're assuming that the force is being applied tangentially to the disc. So we would have F of the motor multiplied by r divided by 8 should balance the torque produced by 0.4, which is the friction, multiplied by r. Now r with r cancel, then F motor would be 8 multiplied by 0.4, and that would be 3.2 newtons. Now that would represent the torque produced by the motor in which it balances the friction, which is somewhere here. So that would be 3. So at this particular instant, given by 5 seconds, both torques produced by the motor and the friction, they balanced. So previously, the torque produced by the motor was greater than that. After that, torque produced by friction would be greater than that compared to the motor, which means the speed or the rotational speed of the disc will start to decrease. So after 5 seconds, there will be a decrease, which means that if you look at the question carefully, they're asking us during which time interval does the rotational kinetic energy increases and then decrease. That would be C, because for sure from 3 to 5, there will be an increase. After that, directly we have a decrease. Okay, so if you choose, for example, D from 5 to 7, we know that from 5 to 7, it's decreasing. Then after that, it's also decreasing. From 0 to 1, it is increasing, and after that it's increasing also. Similarly for B, so the correct answer would be C. And finally, the last exercise for today's video, exercise 4. Two uniform spheres X and Y roll without slipping along the horizontal surface as shown above. So they roll, we have two types of energy, rotational kinetic and translational kinetic. Without slipping, it means that In either case, V would be equal to R multiplied by omega. Sphere Y has 2 times the radius and 4 times the mass and half the translational speed of sphere X. The rotational inertia of a sphere in general is given by half mr square. If ky is the kinetic energy of sphere Y and kx the kinetic energy of X, what is the ratio ky over X? So ky over kx, so here they're talking about the ratios of the kinetic energy. They didn't mention which kinetic energy they mean specifically, so we need to include both translational and kinetic. So that would be half. The mass of Y is given by 4m, and its speed is given by half v, plus half the moment of inertia is given by half mr square, and omega is given by half v divided by 2r divided by the energy of X, which is half mv square, plus half the moment of inertia is given by half mr square, and omega is given by v over r, and that would be to the power 2. Now this would cancel, so now we would have, now this would cancel with the 4, so we would have half m v square plus, now half to the power 2 would cancel with these two, and we would have, now r would cancel as well, so let me do it again carefully. So this would cancel with these two, r would cancel with r square because we have to the power of 2, and that we're left with 1 over 4 mv square divided by half mv square plus, so half with a half, that would give us 1 out of 4. Now mv square, and you can notice that both they are equal, so that would be 1, and remember that this is a dimensionless ratio, making E to be the correct answer. Then that's it for me in this video, guys. See you soon in a new one.